Hello and welcome to part one of the Finding Real Roots of Polynomials Equations lesson. Due to the excessively long lesson we have here, I think there's 7 examples. I think we're just going to do 3 on this video, and then I'll do another video with examples 4, 5, 6, and 7 for another day, because y'all know y'all don't want to watch a half-hour video and I don't want to make a half-hour video. So let's just go ahead and look at the first few examples of this lesson based on what we did today. We did a discovery activity today, and I'm going to refer to that a little bit. First of all, on your lesson, I want you to take note of a little bit of the terminology here. This is a polynomial function can be written as f of x equals a sub n times x to the n plus a sub n minus 1 times x to the n minus 1. And this is what I wrote on the board for you to copy onto your discovery activity today. So I want you to highlight this. If you don't have a highlighter out, go ahead and pause your video and go get a highlighter. When you come back, highlight the polynomial function and that it can be written in this form. Go ahead and highlight this whole thing. The reason I want you to highlight this whole thing is because at the end, it shows you the a sub 1 to the x plus a sub 0. So it counts this down as in standard form. So make sure that you highlight both of those. The second thing is looking at this polynomial in behavior box down here. You can see that there are 4 columns, and hopefully you'll notice that I have cut and pasted those onto the polynomial in behavior sheet that we did in today's activity. So this is today's activity. You should have everything on your paper like I have on here. So this is the key to it. You want to pause that, flip it over and show you the other side. There's that side of the key. And hopefully you recognized that when the degree of the polynomial is odd and the leading coefficient is positive, that it behaves a certain way, and so on and so forth. And we're going to work with that in this lesson today. So if you didn't get that, you still need those, then go ahead and pause or rewind it, and you can look at that a little bit further. But to make this try to not last all night, I'm going to go ahead and push up and look at the paragraph on the bottom. Here the bottom says, you know how to use transformations to help you graph functions of this form, f of x equals a times the quantity x minus h to the n power plus k. This is vertex form. Hopefully you recognize it. And I want you to add a couple of notes to the bottom of this sheet to help you remember how transformations work with this. Remember, this is probably the part that should jump out at you the most. This plus k over here represents a vertical translation. This is what was written on the board for, probably the first couple of months of school. Vertical translation. Remember, if it's positive, it's moving up, and if it's negative, it's moving down. Please make that note. The second thing in here is the h value. This represents a horizontal translation. Horizontal translation. This is where it's sliding left to right. And remember here, if it is positive, it's moving to the left, so it seems backwards. And if it is negative, it is moving to the right. But the reason it seems backwards is because of the x minus h in here. The last piece on here to point out is the a out front, and remember that represents compressions and stretches. And there is so much about compressions and stretches that you are welcome to look back at your notes for, but we'll just leave it at that as far as adding notes to this sheet. If you don't have those down yet, go ahead and pause it so you can get those down. I am moving on. Okay. Looking at the back of this sheet, this talks about 4 different degrees. Degree 1, of course, is linear. Here we're talking about an equation like f of x equals x plus 3, something like that, where it cross at a positive and have a positive slope. Here we're talking about a degree 2, which is a parabola. This is a quadratic. Degree 3 is called cubic, and remember degree 4 is called quartic. Pay attention to the behavior of these graphs. This is a positive degree, and it is going both the first and second quadrants. So as x is getting bigger or moving to positive infinity, the y values are going up, which is moving to positive infinity as well. And as x moves to negative infinity, or going this way forever, the y value is also going to positive infinity. Okay? Notice on degree 1 where you have an odd degree, as x goes to positive infinity, the y values go to positive infinity. But as x goes to negative infinity, the y values are also going to negative infinity. Okay? Here on the degree 3, which is cubic, notice this is also an odd. So the relationship is the same here. This arrow right here is telling you which way it's going to keep going. As x goes to positive infinity, so will y. As x goes to negative infinity, so will y. Negative infinity and negative infinity, this of course is quadrant 3. Positive and positive, of course, is quadrant 1. And degree 4, again, notice that this, again, is an even number for the degree. So it has the same behavior as a degree 2, a quadratic. Now, how many times it shifts also is part of this. Notice that degree 2, but this graph changes direction one time. It's going down, and then it changes direction and goes up. Here, this is degree 2, but it changes direction 2 times. It's actually going down here. But it changes directions here and then here. This is a degree 4, and it changes directions 3 times. It changes directions here, starts going up, and then here, it starts going down, and then here again, it starts going back up. So whatever the degree is, one less than that is how many times the graph will change direction. All right? Let's look at the reflection questions. Let's look at the second reflection question. This says to describe the end behavior of negative 2x cubed plus 3x squared minus x minus 3. Hopefully you've ascertained by what we've done today that that first term is really the only thing that you need to look at here, right here. Now it's x cubed, so the x cubed tells us that it is going to look like the graph just above you. If you look up there, it's going to look kind of like this. But this negative 2 tells us that that reflects. So the negative 2 leading coefficient tells us this is going to flip. It reflects over the x-axis, so what we're actually looking at is this graph. Pause that if you need to. And we'll talk about nested form. Example 2 is about nested form. The nested form polynomial has a form of, and then they write this out in a bunch of different letters. The example helps you understand this a whole lot better. This says to write x cubed plus 2x squared minus 5x minus 6 in nested form. So starting with the function, we're going to start from the end. And we're basically going to take out this portion, the x minus 6, and put us over here. What you're doing is you're factoring an x out of the first 3 terms. So when I factor an x out of the first term, I end up with x squared. When I factor an x out of the second term, I end up with 2x. And when I factor the x out of the third term, I end up with negative 5. Then we're going to do it again. This time, we're taking this portion out. We put an x minus 5 here, which is effectively factoring x out of these first 2 terms, leaving me with x plus 2. So, this is my nested form. And we're going to use that again in another problem in just a minute. This is to use the standard form and the nested form to evaluate the polynomial for x equals 3 and then compare both methods. And it wants to know which one that you think is easiest. It may not be the one that they think is easiest. So if I take the original equation, x cubed plus 2x squared minus 5x plus 6 and substitute the 3 in, I've got 3 cubed plus 2 times 3 squared minus 5 times 3 minus 6. Okay? So this is standard form. And if I take the nested form, then I've got the parentheses, 2 parentheses. Then I'm substituting a 3 in for every x. So I've got 3 plus 2, close parentheses. Then I've got 3 minus 5, close parentheses. Then I've got 3 minus 6. So this is your nested form. So let's work on both out. Here, 3 cubed, hopefully you remember, 3 times 3 is 9, times 3 is 27. Plus 3 squared is 9, times 2 is 18. Minus 5 times 3 is 15, and minus 6. Finished in the math here. 27, 18, 20, 30, 45. Minus 15, minus 6, and 45 minus 15 is 30. Minus 6 is 24. Hopefully you can still see that. I can still see it on my screen. And let's look at this one over here. 3 plus 2 in parentheses. We've got 5 now. If I bring down this times 3, then I have 15. If I bring down this negative 5 or minus 5, then I have 10. If I bring down this times 3, then I have 30. And then if I bring down my minus 6, then I've got 24. If that's more confusing for you, then just keep doing this. If the exponents are more confusing for you, then you're welcome to use the nested version. If you want to pause that, rewind it, watch it again, please do that. Don't rush this. If you're confused, watch it again. Or come to intervention and let me help you. All right? Let's flip it over and look at one more example. Or go to the next page. Here on example 3. Yeah, let's do this page and then we'll be done for tonight. Graphing polynomials. Okay. Same equation. X cubed plus 2x squared minus 5x minus 6. This is to determine the end behavior of the graph. The end behavior is determined by the leading term, just like we talked about a second ago. Remember, with your x cubed, it's going to look like this. So in quadrant 1, as x goes to positive infinity, so does y. And in quadrant 3, as x goes to negative infinity, so does y. So that's what they're asking you for in these two blanks. As x goes to positive infinity, f of x, which is y, goes to positive infinity. And as x goes to negative infinity, f of x, which is y, also goes to negative infinity. You may also note that on the activity sheet that we did today, if you look at the x cubed examples that we did, this is also on there. As x goes to positive infinity, so does f of x. As x goes to negative infinity, so does f of x. And that's on there for every one of your reversions here. You're welcome. Okay. So this says to complete the table of values, and it says to use the nested form from the previous example to evaluate the polynomial. So let's look at nested form again. Remember, the nested form of this equation was x plus 2, close parentheses, x minus 5, close parentheses, x minus 6. Okay? We only need that last one. So substituting these values in here may be a little bit easier now. Negative 3 plus 2 is negative 1 times negative 3, because you're putting x in there also, gives you a positive 3, minus 5 gives you a negative 2, times negative 3 gives you a 6, minus 6, which gives you 0. Okay? Another way to do this, a little bit quicker, so I know speed is a big thing for you guys, is to substitute, or go ahead and plug in the equation into your calculator, And you can plug in this equation right here into your calculator. You can plug in x into y equals x raised to the third power plus 2x squared minus 5x. See what I'm doing? Just plugging it into the y equals. Minus 5x minus 6. Got it all plugged in there. Then I'm going to hit second and graph, and it takes me to the table. So then I can use this table to copy values into the table on the screen. Okay? Or you can keep plugging it into the nested formula, or you can keep plugging it into the f of x formula, or the standard form. So we should get that when x is negative 2, f of x is 4. And if you want to try this on your own to make sure that you can get it, which would be a great idea, pause it. And then unpause it, and you can see if you got it. Where x is negative 1, when you do the math here, you get 0. When x is 0, when you do the math, you get negative 6. When x is 1, f of x is negative 8. When x is 2, f of x is 0. And when x is 3, f of x is 24. Okay? So then it asks us to plot the points from the table on the graph, omitting any points whose y values are much greater than or much less than the other y values on the graph. So which one are we going to eliminate? Hopefully you see that we're not going to worry about graphing that. We're just going to graph the other points. Okay? So where x is negative 3, y is 0. Where x is negative 2, y is 4. Where x is negative 1, y is 0. Where x is 0, y is negative 6. It's down off the screen that I'm showing here. Where x is 1, it's negative 8, that's even lower. Where x is 2, y is 0. So you end up with, and I'm going to need to show this a little further up, so I'm going to scoot this up and do this again. But just that portion. So we're not here all night. All right, let's look at this to where you can see the graph a little bit better and think about the reflection questions. Okay, we had coordinates negative 3 and 0. We had negative 2 and 4, negative 1 and 0, 0 and negative 6, 1 and negative 8, 2 and 0, and then the 3 went up really high. So when we connect these, we end up with graph that looks like this. Oops, I missed the mark. You get the picture. Okay, so think about the behavior of the graph and the equation therein. You can also do this on the calculator and look at the graph. We already have the data in there, so if you just want to hit graph now, then it'll graph it. You can compare it to the graph that we have on the board or the graph that you have on your worksheet and see that we did pretty well there. This wants to know what are the zeros of the function and how can you identify them from the graph. Well, hopefully you remember that zeros of the function are where it crosses the x-axis. So we have those at negative 3, and we have one at negative 1, and we have one at positive 2. And how can you identify them from the graph? Well, they're where they cross the x-axis. Where the graph crosses the x-axis. Okay? A couple more questions and we're done for the night. 3b says, what are the approximate values of x for which the function is increasing? For the function is increasing. So the function is increasing along this interval and then along this interval. So if you think about the x values where that's happening, well, it starts going down where x is negative 2. And it starts going back up again where x is a positive 1. So let's think about those intervals. It's decreasing where x is greater than negative 2 and less than 1. So it's increasing where x is less than negative 2 and where x is greater than 1. And you can use infinities to represent that as well. You could use greater than negative infinity here. Okay, and you can use a less than positive infinity there. I'm not sure how comfortable you guys are using infinities yet, so we don't necessarily have to go there. K3C says a student wrote that f of x has a minimum value of approximately -8, and do you agree or disagree? Well, if you look at the graph here, they're saying that the graph bottoms out here where y is -8, which is true at a local level. But look at the rest of the graph here. We know that it's going to go down forever with a negative infinity from here. So we should disagree because of the behavior of the leftmost end of the graph. And the last question, without graphing, what do you think the graph of g of x equals -x cubed minus 2x squared plus 5x plus 6 would be? Well, hopefully with the starting with the negative, you would expect it to be a reflection over the x-axis. So without me writing that on the board, go ahead and add that to your worksheet, which is another way I can see whether you watched the video or not. Have a good night.